To find the zeros of a polynomial function, the main idea is that we need to factor the polynomial completely. Now, some higher degree polynomials are not going to factor using the traditional methods, so this algorithm outlines a process of using what we call the potential rational zeros list and then cross-referencing that with the x-intercepts of the graph to come up with realistic candidates for zeros and therefore factors that can be divided out of the original polynomial, which then enables us to factor it. So let's look at an example and we'll come back to these steps as we move through it. Here we have a fourth degree polynomial which does not factor using grouping or any of our traditional methods, and we're asked to find the zeros of the polynomial. We're going to find all the zeros, both real and complex, and so right away we know that because the degree of this polynomial is 4, we can expect to get 4 zeros, but we don't know if they're real or complex or maybe even perhaps repeated. So in order to begin, the first thing that we want to do is to get the list of potential rational zeros, which is also sometimes referred to as the P over Q list. As a reminder, P is the constant and Q is the leading coefficient, and we're interested in getting all of the factors of P, which are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18, and we want to find all combinations of the factors of P over the factors of Q, which are plus or minus 1 and plus or minus 3. In order to ensure that we get a complete list, we need to proceed in an organized way. We start with the first factor of Q, and we'll write every factor of P over that first factor of Q. Since that's all factors of P over 1, all the factors of P are going to be in the P over Q list. This is all the factors of P over 1. And then we move to the second factor of Q, and we're going to write all the factors of P over 3. So we get 1 over 3, 2 over 3, 3 over 3 is 1, but we already have 1 in the list, so we don't need to duplicate that. 6 over 3 is 2, and we already have that. 9 over 3 is 3, and we already have that one. And 18 over 3 is 6, but again, we have that in our list already. So this is our complete P over Q list, and the next thing that we want to do is to cross-reference this P over Q list with the graph to find good candidates for our real zeros. So let's come back over here to our calculator and input our function. So let's enter this and then go over to our graph. And it's hard to see what's going on here. We could manipulate the window to get a better picture, but we're mostly interested in where this graph appears to cross the x-axis. These are good candidates for my real zeros. And if they're also rational, they would be in this list of potential rational zeros. It looks like my graph is crossing at -2, and -2 is in the list, so that's a good candidate. It also looks like we're crossing somewhere in between 0 and 1. We've got 2 rational numbers that are in between 0 and 1. We could zoom in here a little bit more, but it does appear that that 0 is a little closer to the y-axis than to x is equal to 1. So I'm guessing that x is equal to positive 1/3 would be another good candidate. We could even get a quick confirmation by checking to make sure that these are x-intercepts using second calculate value. Quickly checking to be sure that -2 is a 0, we see that it actually is an x-intercept, so this is going to turn out to be a 0. And then we could also do the same thing for 1/3, which is an x-intercept, so these are absolutely the candidates that we want to use in our synthetic division. Now the graph has been extremely helpful. We see that we have 2 real zeros, we know where those are, but we were asked to find all the zeros, and there are 4 of them. So our suspicion is that we're going to have 2 real zeros and likely 2 imaginary zeros. We can see the real ones on the graph, but in order to find these 2 imaginary zeros, we must factor this polynomial. And this is where we use the real zeros to help us get it factored. We're going to use synthetic division to divide out those linear factors, which helps us to chop down that 4th degree polynomial, and that's a necessary step to finding the imaginary zeros. So we'll start with x is equal to -2, which we've seen is a 0. And if x is equal to -2 is a 0, then x plus 2 must be a factor of the original polynomial. which means that x plus 2 divides evenly into that original polynomial. So what we're about to do is to divide out the x plus 2 factor, and whatever we get as a quotient will be the other factor. Because our divisor is linear, we can use synthetic division, which means to start with this backwards L box. We're going to put the 0 of the divisor into the box, which is also the 0 that we're testing or verifying. And the coefficients of the dividend are listed to the right here. The dividend is our original polynomial function that we're dividing into, so we'll bring these coefficients into that synthetic division problem. We draw a line here, leaving a lane of space for some work, and begin the synthetic division. First we bring down the 3, and then multiply on the diagonal to get -6, combine down to get -1, multiply on the diagonal to get +2, combine down to get 27, multiply on the diagonal to get -54, combine down to get -9, and then multiply on the diagonal to get +18. And when we combine down here, we see that we have a remainder of 0. Since our goal is to get the polynomial factored, every time we get a 0 remainder, this is where we want to pause with the synthetic division and start factoring the polynomial. These coefficients down here are going to be the coefficients of the quotient. And this quotient is going to be the factor that remains when we divide x plus 2 out of the polynomial. Remember, the goal is to completely factor this polynomial so that we can find the zeros. We started with a 4th degree polynomial and just divided out a 1st degree, which means that that quotient must be a 3rd degree polynomial. So 3 is the coefficient on x cubed minus x squared plus 27x minus 9. So we have 3x cubed minus x squared plus 27x minus 9. Now we have two possibilities from here. One thing that we could do is notice that this actually does factor by grouping now. So we don't really need the graph or the P over Q list to help us factor from this point. The other possibility is to use the 0, x is equal to 1/3, and continue to factor using synthetic division. But this time, I'm going to factor this by grouping, which means we're done with that P over Q list. So we begin by copy-pasting the x plus 2 factor, and I'm going to add in a large bracket because I don't want to have too many sets of parentheses. So I'm going to turn my outer parentheses into brackets, just for delineation, and then factor by grouping what's inside here. So we'll group the first two terms together and see that what we have is an x squared that's in common. So we pull that out and get 3x minus 1 that remains. The second two terms have a 9 in common, so we factor out the plus 9 and we get 3x minus 1 that remains. So for our next line, we just copy-paste the x plus 2 factor. Now, because we have this 3x minus 1 common factor here, we're going to pull that out so that what remains is x squared from the first grouping and plus 9 from the second grouping. And now that I have it completely factored, I no longer need this outer set of brackets because everything is just being multiplied together. So our polynomial is now completely factored. Notice this is a quadratic, but it doesn't factor over the reals. It doesn't factor using any of our traditional methods. So once the polynomial is completely factored, however we need to do that using the PQ list, factor by grouping, factor using a traditional method, we have a lot of tools for factoring polynomials. Once we get it completely factored, then we want to set each factor equal to 0 and solve for x to get all of the zeros for this polynomial. So we plug in 0 for y and solve for x by setting each factor equal to 0. Solving these two equations give us the real zeros that we saw on the graph at the beginning of the problem. It's this irreducible quadratic that we needed to find in order to get those remaining two imaginary zeros. So we'll subtract 9 from both sides. To get x squared is equal to -9. We take the square root of both sides and apply a plus or minus onto the constant side. So x is going to be equal to plus or minus the square root of -9 is 3i. Notice that we had two real zeros and two imaginary zeros, giving us the 4 zeros that we were expecting from this 4th degree polynomial function.